In this tutorial, we will be discussing the elements in the periodic table. Elements are defined by the number of protons. It is the number of protons in the nucleus of an atom that identifies it as the particular element. The number of protons in the nucleus of the atom is given by the atomic number and a symbol Z. The periodic table of elements lists all of the known elements according to their atomic number. So this number up here is the atomic number. Now be careful of overgeneralizing because periodic tables are depicted in different ways. Sometimes this number will be on bottom, sometimes the number will be on the bottom left, upper left, bottom right, whatever. You're going to look for the whole number. There's two numbers on here. There's the atomic mass, which is all the isotopes that are averaged together based on their relative abundance, and the atomic number, which is the number of protons. The number of protons, the atomic number, will always be smaller, and it will always be a whole number. Sometimes the atomic mass is a whole number, but these are elements that only occur in fleeting amount of time. They can't get a really good accurate weight on it. But most of the time, the atomic mass is a rounded off number, and it has a decimal place. The atomic number is the number of protons, and it's the whole number, and it's the smaller of the two numbers. Most chemical symbols, which is also another thing you see here on the periodic table, those are the letters, are based on English name of the element. However, some are based on Latin names. For instance, potassium is a K rather than a P because it's from the Latin word kalium. Or the symbol for sodium is Na rather than S because of its Latin name natrium. Other elements with symbols based on Greek or Latin names include lead, which is Pb, mercury, which is Hg, iron, Fe, silver, Ag, tin, Sn, and copper, Cu. Notice that every single time there's two letters, the first letter is capitalized, the second letter is lowercase. That also becomes important because it helps you to identify which element we're referring to. So if we say that we have Cu versus Cu, or CO versus CO, we know that this is cobalt because of the lowercase o, where this is carbon monoxide because there's two uppercases. So I have two elements here. A capital letter signifies the start of the next element. Keep that in mind because that's going to come in handy as you go through the chemistry. Early scientists gave newly discovered elements names that reflected their properties. For instance, argon came from the Greek word argos, which means inactive, referring to argon's chemical inertness, the lack of reactivity of argon. Other elements are named after countries: polonium for Poland, francium for France, and americium for the United States of America. While other elements are named after scientists. For instance, curium is named after Marie Curie, a chemist who helped develop radioactivity and also discovered two elements, and later on won 2 Nobel prizes for her work. Bromine originates from the Greek word bromos, which means stench. Bromine vapor, seen as the red-brown gas in this photograph, has a very strong odor. Alright, so let's now look at our periodic table. You really need to familiarize yourself with the periodic table itself because you don't want to waste your time looking for things. So you don't want to look at an alphabetical list. You want to look at the periodic table itself so that way you can see where things are positioned because that's going to help you more in the long run. So which element has a chemical symbol of Pb? Look on the periodic table for Pb, and you'll find it right here. Notice that not only does it give you the symbol the atomic number, and the mass, it also tells you written out that it's lead. Now remember, each periodic table tells you something a little bit different. It's not always exactly the same. I've seen several periodic tables that don't write out the name of the element for you. And you just have to know instinctively that Pb is lead just by the fact that you've seen it so many times. Alright, so what is the chemical symbol for potassium? Look at all the words, and you find that potassium is right here with the symbol of K. Both Pb and K, lead and potassium, are things that we had discussed in previous slides of this particular tutorial. But I wanted to make sure that you were able to scan the periodic table and look for these. So how exactly was the periodic table designed? Well, Dmitry Mendeleev, a Russian chemistry professor, proposed from observation that when the elements are arranged in order of increasing relative mass, certain sets of properties recur periodically. So here's his version of the periodic table. Here's the modern version of the periodic table. He's credited for creating the, quote, modern periodic table. And you'll see why. If you notice here, let's say we have, look at this row here. LI, NA, KRB, cesium, so on and so forth. If we flip this 90 degrees, we will see that Li, Na, KRB, cesium are on a row here as well. We could do the same thing. I dropped my pen, I apologize. Right here with boron and aluminum. So you can see how things match up. If we look here, carbon, boron, carbon, nitrogen, oxygen. Boron, carbon, nitrogen, oxygen. So it's just basically flipped 90 degrees, and he did this with very little additional work. He grouped things by how they're reacting with each other and their physical and chemical properties. He was the first one to base it more on that than on the mass itself. Even though when you line them up by mass you will see repeating properties, he strayed from this occasionally. So if we look here, tellurium and iodine, tellurium is 127 while iodine is 126. So that feels like it's out of order, but because of its reactivity properties, he kept them in that lineup just for that reason. Mendeleev's periodic law was based on observation. Like all scientific laws, the periodic law summarized many observations but did not give any underlying reason for the observation. Only theories do that. For now, we accept the periodic law for what it is. But in Chapter 9, so in the future tutorials, we will examine the powerful theory that explains the law that gives the underlying reasons for it. So if you're not following this particular book, just know that in future tutorials, it'll talk about why the periodic law exists. The theory behind it. So let's look at other ways that it's been organized. The elements in the periodic table can be broadly classified as metals, nonmetals, and metalloids. Metals occupy the left side of the periodic table and have similar properties. They're good conductors of heat and electricity. They're malleable, meaning that you can pound them into flat sheets. They're ductile, meaning that you can draw them into wires. Lustrous, meaning that they're shiny. Metals tend to lose electrons when they undergo chemical changes. So if we say that electrons are -1 charge and we're losing electrons, so we're minusing a -1, it actually becomes positive, which means that they form cations, because cations are positively charged ions. And good examples of metals are iron, magnesium, chromium, and sodium. Nonmetals are on the upper right hand corner of the periodic table, plus hydrogen. Don't forget about hydrogen on the left. The dividing line between the metals and nonmetals is zigzag line. diagonal line running from boron to astatine. Nonmetals have more varied properties. Some are solids at room temperature, while others are gases. As a whole, nonmetals tend to be poor conductors of heat and electricity. In other words, they're more insulators. Nonmetals tend to gain electrons when they undergo chemical changes. So we're gaining electrons, so we're adding -1 charges, which means that when they form ions, they form negative charges. These are anions. A-N-I-O-N, if you can't read that first writing. Good examples of nonmetals are oxygen, nitrogen, chlorine, and iodine. Metalloids lie along the zigzag diagonal line dividing metals and nonmetals. Metalloids are also called semimetals and display mixed properties of both the metals and the nonmetals. They're also called semiconductors. So metalloids have 3 names: metalloids, semimetals, and semiconductors. They're called semiconductors because of their intermediate electrical conductivity, which can be changed and controlled. This property makes semiconductors useful in the manufacture of electronic devices that are central to computers, cell phones, and other modern gadgets. Silicon, arsenic, and germanium are good examples of metalloids. So looking at patterns in the main group elements whose properties can generally be predicted based on their position, and transition metals whose properties are less predictable based on their position. So if we're looking at patterns, the first row tends to lose 1 electron, making it a +1 charge. The second one tends to lose 2 electrons, because they're all trying to be like the noble gases, which are inert. They don't react. Group 3A tends to lose 3. Notice group 4 is halfway to 8. So it can go in either direction. Then group 5A, instead of losing, it ends up preferring to gain electrons, making it a -3. Group 6 is a -2. Group 7 is a -1. And group 8 is 0. Those are the charges that they create when they react to form ions. The transition metals, however, aren't so strategic. They can have several different charges. The periodic table with the groups highlighted, the alkali metals, alkaline earth, halogens, and the noble gases are going to be talked about in the next few slides. So, alkali metals are the very first row, and they include lithium, sodium, potassium, rubidium, and cesium. They're very reactive with water, which is why you'll see right here sodium's on fire. Alkaline earth metals are also fairly reactive, and they are the second row on the periodic table. They form a +2 charge when they react. And they include beryllium, magnesium, calcium, strontium, and barium. Group 7A tend to gain 1 electron, making it a -1 charge when it reacts and forms ions. The halogens include fluorine, chlorine, bromine, iodine, and astatine. And finally, the noble gases are group 8A, which include helium, neon, argon, krypton, and xenon. They're the last row on the periodic table, and they're pretty much inert. There are some exceptions, but they do not react nearly as much as the other ones. And that's what the other atoms want to gain and lose electrons to be like, because they want to be inert as well. So, let's do some practice problems with these. Which of the following elements is a metalloid? So we're looking for an element that's on the zigzag line. Aluminum is here. Silicon is here. Tin is here. Phosphorus is here. and iodine is here. They're all very, very close. The only one that's actually on the line are aluminum and silicon, so we'd have to choose between those two. If we go back to our picture here, notice that aluminum is technically considered a metal even though it's touching the line, while silicon is considered a metalloid. So that means our answer will then be silicon. Strontium, which is right here, is in which of the following groups? Halogens, which are here. Noble gases are here. Alkaline earth metals is actually where it is. It's in the second row. Alkali metals are here. And these are the transition metals. And then finally, chlorine, which is here, is in which of the groups? Once again, halogens are here, which is the group it's in. Noble gases are here. Alkaline earth is here. Alkali and transition metals. This is primarily memorization. There's really no other way to go about it than to memorize which rows are which. And that is how the periodic table is organized.